Lesson 6.1, Approximating Areas with Riemann Sums. Let's take a look at the relationship between the graph of a rate of change function and the area of the region between that derivative graph and the x-axis. Consider the tropical cyclone Imelda that brought more than 40 inches of rainfall over a 72-hour period in southeast Texas during September 2019. Example 1. In order to avoid floodwater entering your home, you rent a pump that can remove water at a rate of 500 gallons per hour for the first 8 hours of pumping. As the storm grew stronger, you got a second pump, and for the next 16 hours, you could remove 900 gallons per hour using 2 pumps. Draw a graph that models the removal of stormwater from your property. Label the axes correctly. So, what we're going to do is we're going to look at, for 8 hours, 500 gallons of water was pumped. So this is going to be our time in hours. And this is going to be our gallons of stormwater. And so since 500 times 8 is 4,000, this is going to represent 4,000 gallons of stormwater that is being removed. Then from hours 8 to 24, you added another pump, and then 900 gallons of stormwater was being pumped. So 900 times 16 represents 14,400 gallons of stormwater. So that's what that would look like. Now think of gallons of stormwater per hour. That is a rate, okay? When your y-axis is a rate, and you look at the area under the curve, that is going to be, so if your rate is always, something over something. So this one was gallons of water, and then this means per hour, okay? That was your rate, and that was the y. That was on your y-axis. That was the units of your y-axis. And then you have, of course, time in hours. So when you calculate your 4,000, which is your, your 8 times 500, that just gives you gallons of water. So you are always going to have the numerator of your rate when you calculate your area under the curve. Okay, so when I'm calculating this area, and here's my curve. I'm going to put my curve in pink. That's my curve. That's my curve. Okay? So when I'm calculating the area under the curve, and I calculate, 4,000 here and 14,400 over here, that is going to be the y value of your numerator. So you had 4,000 gallons of water that was pumped out in the first 8 hours, and then 14,400 gallons of water that was pumped out in the next 16 hours. And so total of 14,800 gallons of water. So when we say area under the curve, this represents the area between the graph and the horizontal axis. So it's between the graph, this pink graph, and the x-axis. Find the area under the graph from 0 to 8. What does this value represent in context to the tropical storm Imelda? So since we found the 500 times 8 was 4,000. We said a total of 4,000 gallons of stormwater was removed during the first 8 hours of pumping during Imelda. So that was the first 8 hours of pumping during the storm Imelda, okay? Find the total area under the graph for the entire 24-hour period and explain the meaning and context to the scenario. So we had the 4,000 plus the 14,400 for a total of, 18,400. I think I said 14,800 up here when I did my total, but I meant 18,400. And this would be explained in 24 hours of pumping stormwater during Imelda. We want to be very specific so that we are, for this particular situation, a total of 18,400 gallons of water was removed from the property by pump. Okay. And this is, they want to make sure you understand what happens when you find the area under the curve. And it's going to be a little bit of writing coming up here in some of these problems. So what approach can we take if the rate of change function is not constant? The two big ideas in calculus are the tangent line problem and the area problem. In the tangent line problem, you saw how the limit process could be applied to find the slope of the tangent line, the derivative, at any point on the curve. A second classic problem in calculus is in finding the area under a curve that is bounded by the graph, the x-axis, and any two x values. A basic overview of areas as limits. In the limit of rectangles approach, we take the area under a curve y equal f of x above the interval AB, closed interval AB, by approximating a collection of inscribed or circumscribed rectangles in such a way that the more rectangles used, the better the approximation. Finally, the number of rectangles is increased without limit, and bingo, we get the area, now known as integration. So specifically, we are interested in finding the area A of a region bounded by the x-axis, the graph of the non-negative function y equals f of x, defined for some closed interval AB. Note, the requirement that f be non-negative on AB means that no portion of its graph on the interval is below the x-axis. By using rectangles, we can see that there are 3 different ways of approximating the area for A. This method is commonly known as Riemann sums. Okay, so we're gonna talk about all the different ways to calculate, and we're gonna be doing an approximation for the area under the curve. Okay, some of them are gonna be, more than what you actually have. Some of them are gonna be less than what you actually have. Consider a 30-gallon aquarium is being filled with water at a rate modeled by R of t equals 6 sine of pi over 8t, where t is time in minutes and R of t is gallons per minute. Find the volume of water in the tank after 5 minutes by using 5 rectangles that are 1 minute wide and R of t in height. So what we're going to do is we're going to make a chart. We're going to make a T, R of T chart. Okay, so we're going to look at, 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, and see what the approximation is, or actually we'll probably, since we actually have R of T here, we're going to put it in our calculator and get that approximation. We're going to take, 6 times the sine of pi over 8. For this, for t equals 1, because it would just be pi over 8. And we're going to get 2.296. And so at 1, it should look like about 2.296, and I do see that. At 2, we're going to take 6 times the sine, and this one would be pi over 4, because when I put 2 in, I get 2 pi over 8, which is pi over 4. So 6 times the sine of pi over 4 is going to be 4.243. And when I look here, there's my 4.243 about right there. And at 3 will be 6 times the sine of 3 pi over 8. And that should give you 5.543. And then we look up here and we see that at 3, that does look about like 5.543. And then we put a 4 in and we say 6 times the sine of 4 pi over 8, which would be 6 times the sine of pi over 2. That's just going to be 6. And since I'm writing them all with 3 places behind the decimal point, I'm just going to write that one also with 3 places behind the decimal point. And there's my point right there. And then at 5, I would be calculating 6 times the sine of 5 pi over 8, and I should get 5.543. And there's that one. Okay, so we've seen them on the graph, and those are your y values. Of course, at 0, you had 0. So now, after 5 minutes, what we would do is we'd say, okay, I have this y value. I'm going to take this y value and I'm going to move it all the way over and calculate the area of this. This would be 1 times 2.296. So that area is going to be 1 times 2.296 is 2.296. And then for the next one, you're going to take that point, move it over, and call that a rectangle, and you want to find this area. And it's going to be 1, because look, from here to here is 1, and it's just length times width. It's going to be 1 times 4.243. That's 4.243. And then you're going to do the same thing here. Take it, move it across, and then calculate this area. And again, distance, or the length is 1 times the y value, 5.543. Next one, 1 times 6 is 6, and 1 times 5.543 is 5.543. And now you've got an estimation for the area under the curve. If we used more rectangles with smaller widths, we could achieve a better approximation. In fact, if we considered taking this to the limit of and accumulating an infinite number of rectangles, we would arrive at the exact volume of water in the aquarium after 5 minutes. This is called the definite integral, and it's represented by the notation, the integral down here, the integral from 0 to 5, r of t dt. And so this